Back in our discussion of molecules, we spent a considerable amount of time thinking about bonding and the molecular orbitals that result. But how does that work in metals, where we have extended structures in 3 dimensions instead of individual bonds? Well, much of what we learned back then still applies. When we dealt with molecules, we talked about covalent bonding. Originally, this was between 2 atoms. We used molecular orbital theory to mix atomic orbitals and form molecular orbitals. At the end of that discussion, we allowed for the possibility of delocalized bonding, where you could mix atomic orbitals from more than 2 atoms. We can use that same idea in thinking about bonding in metals. Bonding here is usually referred to as metallic bonding. It is between many, many atoms in 3 dimensions. This is generally referred to as band theory. We'll find that the principles from molecular orbital theory are similar to what is used in band theory. Going back to molecular orbital theory, we reproduce the information in figure 6.21 from the textbook. This is a molecular orbital energy level diagram for dihydrogen, with the energy levels and the shapes of the 1s atomic orbitals on the left and right, and the energy levels and shapes of the sigma bonding and anti-bonding molecular orbitals in the middle. We note that 2 atomic orbitals mix to form 2 molecular orbitals, one bonding at lower energy and one anti-bonding at higher energy. We can make the following general statements when atomic orbitals are mixed to form molecular orbitals. Half of the molecular orbitals that are formed are bonding and are at lower energy. Half of the molecular orbitals that are formed are antibonding and are at higher energy. We should expect this result regardless of how many atomic orbitals are mixed together. Let's look at figure 8.7 from the textbook. On the left is the situation where orbitals from 2 atoms are mixed. Rather than draw the shapes of the molecular orbitals, the illustrator has simply drawn 2 blue spheres next to each other to indicate a bonding interaction on the bottom, and a blue and orange sphere next to each other to indicate an anti-bonding interaction on the top, with a vertical black line indicating a node. The energy difference between the bonding and anti-bonding MOs is shown as delta E1. On the right is where atomic orbitals from 10 consecutive atoms are mixed. This should result in 10 molecular orbitals at 10 different energy levels. The illustrator has only included pictures of 3 of the molecular orbitals labeled X, Y, and Z. X at the bottom is completely bonding with 10 blue spheres. The second level, Y, shows 1 node. If you kept going up, the molecular orbitals would contain more and more nodes until you get to the top, labeled Z, where every interaction is anti-bonding. 3 items of note. First, if we draw a horizontal line halfway between the 2 MOs on the left, where we mix 2, we find that on the right, where we mix 10, half of the MOs are at lower energy and will be bonding, while half of the MOs are at higher energy and will be anti-bonding. Second, as you go from 2 to 10, the total range of energies from bottom to top increases from delta E1 to delta E2. Third, although the entire range of energies increases on going from mixing 2 to mixing 10, the spacing between the individual levels gets smaller. Notice how the energy between X and Y, indicated by delta E3, is smaller than delta E1. Now, let's take these ideas to an extreme, using figure 8.8 from our textbook. Notice how on going from 2 to 10 to 20 to 40 to 1,000,000, half of the molecular orbitals that form go to lower energy, while half go to higher energy. The overall range of energies gets larger, but the energy spacings between levels gets smaller. When we get to 1,000,000 orbitals on the right, rather than drawing 1,000,000 lines, the illustrator has simply drawn a box. This is called an energy band. with a multitude of orbitals whose spacings are negligibly small. While in discrete molecules the orbitals are called molecular orbitals, in these extended structures the orbitals are sometimes referred to as crystal orbitals. Ordinarily, in a molecular orbital energy level diagram, we would add arrows to indicate electrons. That would be impractical in an energy band, but how should we indicate the electrons? Well, let's consider how we would do this with one atomic orbital, with two molecular orbitals, or with 1,000,000 crystal orbitals. If the atomic orbitals were empty, the molecular orbitals would be empty. For the band, we would draw a box, but not shade it in. This would be an empty band. If the atomic orbitals have one electron, two molecular orbitals would have two. This is the situation in dihydrogen. Notice half of the MOs are filled. So with 1,000,000, half of the orbitals would be filled, and we color in the bottom half of the band. This is called a half-filled band. If the atomic orbitals are filled, all of the molecular orbitals would be filled like in dihelium. The band would be filled with electrons too. We would color in the entire band to indicate a filled band. Notice how whether a band is empty, half-filled, or filled depends on the electron content of the original atomic orbitals, whether they are empty, half-filled, or filled. We can use band theory to explain conductivity in solids. When we first defined an orbital, we thought of it as a region in space through which an electron is free to move. In a delocalized orbital, such as a crystal orbital, electrons are free to move around over the space of many, many atoms. Although we visualize electrical conductivity as the movement of electrons, random motion in orbitals is not enough. In band theory, the requirement for conductivity is that an electron needs to be promoted from a filled orbital to an empty orbital. We'll go back to our pictures of bands to see how this might happen. For half-filled bands, the highest occupied orbital is called the Fermi level. Given our requirement that an electron needs to be promoted to an empty orbital, not an empty band, it only requires a negligible amount of energy to move an electron from the Fermi level to an empty orbital. Some scientists will speak of the separation of an electron in a hole. A hole is essentially an open spot in what was a filled orbital. It allows the separation of a negative electron and a positive hole, but only requires a negligible amount of energy to do so. This material would be a conductor. What if there are only filled bands and empty bands? There is some language that is used for this situation. The filled band is called the valence band, since this band is filled with valence electrons from the atoms. Now, to get to the next highest level, an electron needs to get to the next band, which is called the conduction band, since an electron needs to get there for conductivity. The energy gap between the top of the valence band, where the Fermi level is, and the bottom of the conduction band is called the band gap. If the band gap is large, this material will be an insulator. If there is no band gap, such that the top of the valence band overlaps with the bottom of the conduction band, it requires no energy to move an electron into the conduction band. This material would be a conductor. If the band gap is small and the population of the conduction band is possible, this material is a semiconductor. The conductivity of semiconductors is temperature dependent. With a small band gap, an increase in the thermal energy can lead to an increase in the number of electrons that can populate the conduction band.